Hi, good morning.
Good morning.
Good morning. Can somebody say something? I'm testing my headset.
Good morning.
Something.
Yeah, the sound is coming from somewhere else. So. Okay, could somebody say something again?
Can you hear me?
Much
Something
better, thank
again?
you. Yep.
Is it working?
Always helpful to hear things, you know. I think I saw Bianca Bushbeck also in the list of attendees.
Yeah,
yes.
she will probably help with the Q&A.
Yep. Okay. So she could be added.
She's already a panelist.
Yes, she's already.
Oh, she already is. Sorry, I don't see that.
Yeah, you have like a blue arrow next, right or left where the panelists are, and you can see more panelists.
Oh, okay. Perfect. Thank you. Okay, good morning, everybody. I am Mary Nordminen, and I'd like to welcome you to day 3 of Eamt 2020. We've had a lot of very good information and discussion so far, and we have one more day packed with all kinds of information and interesting projects to hear about. The first of these will kick off this morning with 3 presentations from the user track. And the first of these is from the people at SAP, who will tell us about how they have experimented with ways to apply terminology constraints to neural machine translation output. So I will turn this over to Miriam XL.
Thank you. I will try to share. All right. You should see my slides now, right? Great. Good. Then, yeah, welcome and thank you for listening and being here. I will report about a study that we conducted at SAP, and it's about applying terminology constraints, as Mary said. And it's joint work with my colleagues Bianca, Lauritz, and Simona. So in case you don't know, SAP is a German multinational software company. Actually, by revenue, it's the largest software company in Europe. However, you might not know SAP, and the reason is that it makes enterprise software. So software to manage business operations and customer relations, for example. And that's why you, as a private end user, might not have been directly in touch with any SAP software. Naturally, in such a multinational company that sells software to the world, there is a high demand for translation as well. And the translation demand ranges from classic translation scenarios like product localization, the translation of software documentation, and other support materials to marketing materials and corporate communication. But really, this is only the tip of the iceberg, because new areas that have not been translated before, because of budget or time or quality concerns, they emerge now. And examples here are customer support tickets and chat conversations. So according to these diverse translation scenarios, we also have diverse translation settings for translating the many product lines that we have. And there are more than 100 active translation domains. And for these translation domains, we also maintain translation memories and terminologies. Now, machine translation is also used. It's used in post-editing settings if we want to have high quality translation. And it's also used raw in other scenarios. We usually train multi-domain neural machine translation models, and the training data for these models consists of a multitude of different data sources, including also the contents of the company internal translation memories from all the various domains that we have. The resulting NMT systems produce high quality technical translations, but they have difficulties generating the appropriate and coherent terminology in the specific different contexts that we have. You can see an example here on the slide. So the system here produces a fluent German translation. Sorry if you don't speak German, there will be many German examples. But the terms that are used here are used from a hypothetical product 1, and it's marked in yellow here, which is just wrong if you want to have a translation that would apply the terminology from product 2 in green here. So human translators, they are assigned a translation project that they have to translate, and alongside with that, also the relevant translation domains terminology that they're supposed to use for translating the translation project. And our vision here is that neural machine translation can apply terminology constraints in a very similar fashion as human translators would do. And here in the example, the terminology constraints would be to use Haushaltsstruktur for budget hierarchy and to use Haushalt for budget. For applying the terminology constraints, we do have certain requirements. So obviously we want to influence the neural machine translation model such that it produces the correct and adequate term translation as provided by the terminology constraint. Then second, we would also like to see the target term in the correct position and morphological form in the translation. If possible, without requiring morphological inflection generators, because it would be hard to obtain them for all the languages that we would like to serve. And finally, also, we don't want to lose a lot of speed in comparison to the regular baseline model. Now, previous approaches that have been around for terminology enforcement, they do not fulfill all of these requirements. So the very simple placeholder approach, where the source term is substituted with a placeholder, and then the placeholder in the translation is resubstituted with the required target term. These approaches, they suffer from disfluency because the NMT model would have difficulties creating a fluent and morphologically sound translation. Then constraint decoding covers a whole class of methods that modify the decoder such that the provided constraint or constraints are strictly enforced in the translation. However, they usually come with an increase in decoding time compared to unconstrained decoding. And also constrained decoding can lead to questionable translation quality, as has been reported in the literature, mostly because the target term is enforced exactly as given by the constraint, and so no morphological adaptation is applied by the decoder. Then last year, an approach presented by Dino et al. At ACL sort of came to the rescue. It should be capable of handling unseen terminology while retaining the ability to produce fluent output that we like neural machine translation for. And it should not have the need for morphological generators, and it should come without drastically reducing decoding speed. So we validated this approach for our scenario. So that's the translation of business and UI and IT, sorry, business and IT content from SAP with terminology constraints that come from the SAP terminology database. We will present some variations of the original approach and also provide an in-depth human evaluation. So here is quickly how the approach works. So the underlying idea is that the model is supposed to learn a copying behavior of the target terminology from the source to the target. This works because the target terms are inserted into the source string during training and during decoding. They can either be inserted right after the respective source term. This is called the append method, or they can replace the respective source term. That's called the replace method. And we've experimented with both methods, and you will see results later. Then, in addition to the term injection, or inline annotation, as you might want to call it, there is also additional term information provided as an additional input stream. In the example on the slide here, we indicated this information with indices. So 0 here means that it's a regular word, 1 means that it's a source term, and 2 means that it's a target term. This information is encoded as a source factor embedding in the input layer of the NMT model. And I'll have a bit more information about that on the next slide. So usually the input to an encoder-decoder NMT architecture are word embedding vectors, or in our case, rather subword embedding vectors. And the concept of the source factors is to generalize those word embeddings to any kind of embeddings that you want to use as input. So then the input word consists of F different factors. In the picture here, it's just 2 factors. where the string, so the word itself, would be just one of them. And then in our application, F1, so the additional embedding here, would be the terminology information 0, 1, or 2. These factor embeddings, they can be combined by concatenating them. That's what you see here on the slide in the illustration. They could also be summed, so they could be added together, but then of course they need to have the same dimensionality. And we've experimented with both, and you also see the results later. So our setup. We have experimented with 2 language pairs, English-German and English-Russian. Both target languages are relatively morphologically rich because we wanted to see whether the approach can indeed produce correctly inflected forms, which was what they had reported in the original paper and which we are interested in. So for data, we used our sort of usual SAP corpora data that comes from our translation memories. And we evaluated on 2 specifically created test sets, one containing at least 1 annotated term in each segment and 1 without terminology at all, sort of as a sanity check. We annotated 10% of the segments in the training and def data with terminology pairs that come from the SAP terminology database. And we annotated if the source term of a pair occurs in the source segment and the target term of the pair occurs in the target segment. For annotation, we use a fuzzy matching strategy to account for different morphological forms in the data, while of course the terminology database only contains the base forms. And as in the original paper, this is a 0-shot setup, which means that we made sure that the terms that were annotated in the test set are not annotated in the training data. For the neural networks, we used the transformer architecture, and we performed all experiments with the SockEye toolkit, just because it has all the features that we needed. Then for evaluation, we will report 2 metrics. There are more in the paper, of course. So to see how well the models adhere to the terminology constraints, we report term rates. The term rate is computed as the percentage of times the expected target term is generated in the machine translation output out of the total number of term annotations that we have in the test set. And here, for the term rate computation and for finding the terms, we also use a fuzzy matching strategy. Then to automatically assess the overall translation quality, we use the BLEU score. And because we are all aware of the shortcomings of automatic evaluation of MT, we also performed human evaluations, and you'll see that the details later. So let's start by looking at the automatic evaluation. You see 4 charts here. It can be a bit overwhelming. So it's the term rate and BLEU for English-German on the left, and term rate and BLEU for English-Russian on the right. And we'll start with comparing only a few of them. So we compare the append and the place approach, each with the concatenated and the added source factors against the baseline. So the baseline does not have any additional term information. And you can see that the baseline already performs pretty good, which can be explained that we are nevertheless in an in-domain translation scenario here. So looking at the append and replace models, they all outperform the baseline in terms of term rate here and in terms of translation quality by a wide margin. There is not much of a difference in the individual methods as reflected in the term rate here and here. But according to the BLEU score, the combination of appending the target terms and concatenating the source embeddings, so that's the dark gray bars here, that seems to work best. Overall, the results show that the approach is effective in improving the translation quality using terminology constraints in our scenario here. So SAP data annotated with SAP terminology. Next, we also trained models without source factors. So we only injected the terminology into the source and didn't use the additional input stream. And somewhat surprisingly, we can observe that the input of the source factors is small for English-German. And for English-Russian, it's basically non-existent. So it seems that the model has learned the code switching that is happening in the source sentence and the intended copying behavior of the injected terms to the output without really requiring this additional input signal. And we hypothesize that the different scripts of English and Russian, so Latin and Cyrillic, are the reason why the model picks up the code switching better for English-Russian than for English-German. And then finally, we also compare against constraint decoding. Here we observe that even though constraint decoding reaches really, really high term rates, here as well, the translation quality really suffers according to Bleu here and even more here for Russian. So here the quality that we can achieve with the append and replace method clearly is superior. That the decrease in Bleu score here confirms observations that have been made in the literature before. And then in addition, it's important to note also that the constraint decoding for us led to an approximate 6-fold increase in translation time, whereas for the append and replace method, there is no such impact. Then we were curious at finding out about the remaining 4% here. So the 4% of terms where the term enforcement did not work as expected according to our calculated term rate. So we manually analyzed a good portion of them from the append concatenation system. And we found that almost half of them are actually false negatives, meaning that the expected translation was indeed produced. And the reason here is that the terms appeared in an inflected form or as part of a compound. And thus the term rate, despite already using fuzzy matching strategies, did not cover them. So from this, we learned that the automatic evaluation, as always with machine translation, is not perfect. And we conclude that the term rate is actually higher than reported by our automatic scores. Then let's quickly talk about human evaluation. So this was a blind study with a subset of our test data with 3 evaluators per language pairs. They were displayed the source sentence, the translation by the respective system, and the term constraint up here in the green box. And it's also, the source term is also highlighted in green. And then the task was to rate whether the translations adhere to the term constraint on a scale from 1 to 6. And we asked them to use the adequacy rating bar here. And also they were asked to rate the general translation quality here on the same scale. For the human evaluation, we used 3 systems, the baseline and the 2 most promising and interesting systems. So concatenation, append system, the append approach with concatenation and without source factors. And in the charts, you can see the average ratings for the term assessment and the general quality assessment for German on the left and Russian on the right. So for the term accuracy in yellow, the baseline clearly lags behind the other two systems. And however, the differences between the no factor and the concatenation approach is small, so we cannot really say which one is better.
Excuse me, Miriam, you have 1 minute left.
Thank you. And for the translation quality, for the translation quality, there is not really a difference here. So the term enforcement at least does not have a noticeable side effect on the overall translation quality. So I brought 2 examples before coming to the conclusion to show how the terms are integrated smoothly into the translation. The first one you already know, so you have the term constraints here you see how the terms are integrated, and also you can see very nicely how the genitive S is added to the target term despite not being in the original constraint. And in the second example, you can see that the terms have also been enforced, which did not happen very well for the baseline, and that the inconsistency here in German is compounded very nicely to the head word here, so to Tabelle, with the respective pronoun, with the respective compounding morpheme. So to conclude, we have investigated an approach for terminology integration into NMT as proposed by Dino et al. Last year. It combines terminology injection with into the source text with source factors. We have evaluated the approach in a real-world setup, so IT-related corporate data from SAP with terminology from SAP. And we've run our experiments, including human evaluation, for 2 morphologically rich languages. We've varied the original approach, showing, amongst others, that maybe the source factors are potentially not strictly required. Our study yielded positive results, namely term rates higher than 95% and overall a good translation quality. So we have confirmed also that this approach can be used. In this approach, the term translations are used very flexibly, and that the required surface form is produced in the sentential context. So overall, it seems to be a promising approach for applying terminology constraints. And before finishing, I would like to make one important side remark. So for using such an approach in production, its successfulness and whether users will accept it will also depend to a very large part on the quality of the terminology constraints that are used at inference time. So usually the term constraints would come from a terminology database or from a dictionary, and then they need to be recognized in the source. So clearly here there is a dependency to the quality of recognizing the terms in the source. And then also the terminology must fit the actual translation project. So it should contain all and only the terms that you want to enforce. And yeah, with this exact approach, also the terminology needs to be unambiguous. But I guess the method could also be extended to make several alternative term translations possible. So obviously we've left out many details here. So here is the link to our paper, if that topic is of interest to you. And with that, thank you for listening. And my colleague Bianca and I will be available for questions now.
Okay, so you're free to put your questions into the Q&A. We have the first one here already. And actually, I had this same question myself. I would have asked it also. So is this approach now in production? Are you using it currently?
To be honest, no. So we're still in an evaluation phase, mostly with respect to what I've mentioned on the right here. So with the question is, do the users actually have good terms that they could inject, and how would that technically work together with all of the sort of surrounding translation tools that are used? Yeah, so we're still continuing sort of this proof of concept.
Oh, okay. How many different terminologies do you have, or terminology sets? You said, I think you have 100 translation memories or translation domains. Does that mean you have 100 different terminologies, or
Bianca, do you want to say something about that?
Yes, I can say something about that. Actually, I have one terminology database, but it is classified by products, actually. So there are very many. And usually when translators launch a translation, they are assigned, let's say, a product category, and they just get the terminology for this product category. So you always have a subset when you translate something for a project. But in general, it's just one database of terms that combines everything.
Okay. All right. Other questions? I'll read this one. Thank you for the interesting presentation. In your last example, it seems that the baseline omitted half of the sentence. While the system injecting terminology has fixed this issue, did you check if this happened in other sentences as well?
Maybe I can also answer this question. So it doesn't happen that often, actually. This was just one of the examples we picked where we have seen a nice integration of the term, but that we lose the term in general is not very often the case. And here in this example, you also see that the reference translation is not really correct. So this is also something you have to keep in the mind. So, but generally, there was also another question in the chat actually about the morphology and whether we checked the cases where the inflections were not correct, right? And here, I mean, we did check that. And it's also the case that terminology often occurs just in the base form in the data we have, because we have a lot of, let's say, UI strings or, yeah, very short strings where you don't see a lot of inflection. So the bigger part of our data was in the base forms, apart from compounding, but this is also most of the time a base form. And inflections occurred maybe in 20% of our data. And here we didn't see a lot of problems, but we didn't actually count them.
Okay, thank you. We would have time for one or two more questions.
Some people are saying that they don't see the questions in the, I can see them as a panelist, but other people don't see them.
Yeah, and I clicked some button, which I don't see anymore, that said that we would answer this live, and I don't know if that makes them then visible. Because now people are saying, somebody said, now I see them. So I'm not sure if people are now seeing them or not. Okay, yep. Yep, but anyway, we have time for another question or two. Here we go. On one of your slides, you have presented the evaluation of the translations. This evaluation was on a sentence level. During this conference, we have learned that the document level evaluation is an approach that might show that the sentence level evaluation might be wrong.
Where's the question?
So I think this is a comment. I don't know if
Well,
they're asking perhaps that, do you have plans to also do document level evaluation?
no, I mean, we totally agree that, so it's right, it was a sentence-based evaluation. We totally agree that evaluation needs to go beyond that. No concrete plans for that specific project at the moment.
Okay, thank you. Final question. Okay, if that's all, then I would like to thank you very much. Wait a minute. Sorry, I had to scroll down to the Q&A. In the cases of terminology errors, were you able to analyze the types of terminology errors that occur? Omissions, wrong terminology, and your terms were consisting of how many words?
Bianca, do you want to take that?
Yeah, actually we did that. And there were cases where the inflected forms were not correct, or yeah, we should look into that. We also found examples where we actually didn't have an explanation why we didn't match the term. We have to admit that this was not very many, and we were not really able to find the reason why this didn't apply. So this is also one of the findings. But most of the times it was really that we didn't match the term because of morphological information that was not present. And sometimes it was a different term that we found, which was still correct. It's like a synonym, but it was not the expected term. And in this case, you have to enforce the term. So this was also counted as not correct.
Okay, I'm going to take the final one then. How practical is this method with a big corpus since it applies to training data?
I mean, there is always a trade-off. So it's practical in the sense that it does not increase training time. But you might want to call it impractical because you need to retrain and make your system learn about the approach. So I guess it depends on your specific use case, what matters more to you. So in the light of the currently available approaches, to us, it seems a very good choice at the moment, especially because the output remains fluent. I think that's the main disadvantage of the other two approaches. But yeah, if you don't want to retrain for the system to learn this method, then of course it's not very practical. But you only need to retrain to sort of learn the copying mechanism. Then you don't need to retrain for new terminology or anything. So yeah, there is a trade-off.
Okay. All right. All right. So I will cut it here so that we can keep to the schedule. I want to thank our presenters and also people who ask questions. And we will now move on. Thank you, Miriam and Bianca. The next presentation is about a project which built an English Swahili machine translation solution, including parallel corpora. And this is going to be described to us and presented to us by Miquel Forcara. So I turn it over to Miquel. Sorry, Miquel, we're not hearing you. You're on mute still.
Sorry about that. I was saying that we will show how we put together an English Swahili parallel corpus and how we used it to generate machine translation systems that would be used in the news domain. This is joint work by researchers at the University of Alacant in Spain and at the BBC as part of the European project Gourmet, which is a Horizon 2020 project. So this is an outline of my talk. After motivating the need for this study, I will explain how we collected monolingual and bilingual corpora, the kinds of neural machine translation systems that we built, how we evaluated them, and I will end up with some concluding remarks. So the motivation is clear. Large news media organizations often work in a multilingual space, which means that they have to either create and publish content in numerous languages or monitor the world's media, which come in different languages too. We hypothesize that machine translation can reduce the required human effort in both scenarios. And this is the main subject of the project Gourmet, which stands for Global Under-Resourced Media Translation. The objective is to build English Swahili and Swahili English neural machine translation systems for both media partners in the Gourmet project, the BBC and Deutsche Welle. Swahili is an important language in Africa, even if it is quite under-resourced. It's the first language for an hard to determine number of people, between 2 and 15 million people, but it's clearly the second language for about 90 million people. It actually works as a lingua franca for East Africa. It's a Bantu language, as many other languages in the area, like Shona or Zulu, Lingala, Kinyarwanda or Kirundi. It uses the Latin script, no diacritics, and the only special sign it uses is the apostrophe in the trigraph NG apostrophe, which stands for the sound, as in ng'ombe, which is a cow. I hope I got it right if some Swahili speaker is out there. Swahili and English are quite different as languages. This is just a selection of some of the problems that you can find, some of the contrast. Like, for example, Swahili has definite and indefinite articles, and Swahili doesn't. English has them, and Swahili doesn't have them. So this would be a challenge when generating English, because you have to put them in the right places. As regards gender, English has only gender in third person singular pronouns, and it's sex-based. So it's a he, she, and it, and that's all basically, and a bit possessives and that. But Swahili has many genders, many different word classes, as they are sometimes called, and generating them correctly is important in Swahili. Adjectives come after the noun instead of before the noun. That wouldn't be a big problem unless the noun phrases are very long. But the problem is agreement, because you have to agree, the adjectives agree with the nouns in as regards the gender and number. Then there's other syntax things, like, for example, to ask a yes/no question. In English, you reorder the affirmative question and you use an auxiliary verb, and in Swahili, you just change the intonation. So in writing, it's just a question mark at the end. And the verb morphology of English is quite poor, with about 5 forms per word, per verb. And in Swahili, you have a very agglutinative and rich verb system, which is sometimes described as a strove, with the acronym STROVE, because it carries information about subject, tense, relatives, object, and extensions for other things, in addition to the verb root. These are the parallel corpora we used in the study. In addition to using the corpora that were available on Opus at the time of the study, which was about 10 months ago, we also added, we're lucky to have access to the SAWA corpus, thanks to the authors of the corpus. And we also collected our own corpus, Gourmet version 1, which I will explain a little bit later by crawling the web. We also use monolingual corpora, as I will show in a minute, and we use the new scroll corpora, which are available in the StatMT website, and we also crawled our own Swahili corpus because the one we had there was too small. So how did we why did we do crawling? Because we found there was very little data to train an English Swahili machine translation system, a neural machine translation system. So we decided to crawl more data. That means to web harvest data using bitexter technology. And we basically went and visited about 4,000 websites, getting the URLs from Common Crawl. And after 12 hours, about 1,000 of them contained a sizable amount of Swahili and English. We only kept the Swahili and English text by using the Common Language Detector number 2. And we ended up having 180,000 documents aligned with their translations. For that, we used a Giza bilingual dictionary and learned on the Opus parallel corpora that had nothing to do with news. And then we aligned the sentences in every document. We ended up having 2 million segment pairs. But we decided to clean this, and we used PyCleaner, as was presented yesterday, on Monday by Gemma Ramirez, or was yesterday, I don't remember now. This is a statistical cleaning model that uses monolingual statistical language models and a regressive or regressor, which is a translation model. And it has to be trained on correct and incorrect alignment examples. So we used Global Voices version 2015 as correct examples. And we randomly misaligned sentence pairs from the same corpus and used them as wrong examples. We use, after selecting the right thresholds for the language model and the translation model, we ended up having 156,000 segment pairs, which means that we threw away 93%, and we hope we didn't throw away the baby with the bathwater, as in the picture. So a nice byproduct of this was that we also collected a monolingual Swahili corpus, which we cleaned using a language model that was trained on Opus Corpora and on SAWA. And we just selected the 6 million lowest perplexity or maximum likelihood sentences. We discarded the rest. And we also discarded sentences that were not Swahili according to the version 3 of the Common Language Detector. And also those sentences that contain more punctuation and numbers than letters. We didn't throw so many, so we have a nice corpus, about 5.5 million Swahili sentences, and it was quite useful, as we'll see in a minute. So for the bilingual corpus, we had to segment it in training, development, and test, as we usually do. So for development and test, we extracted 4,000 sentences at random from a joint corpus made of the Global Voices corpora in Opus. And we split that 4,000 sentences in 2,000 for development and 2,000 for test. And the remaining sentence pairs were used for training. When we were using the neural architecture, we used Marian on that, and we decided to grid search for the best architecture, at least in a certain hyperparameter space. So for example, we checked transformer versus recurrent neural network with attention. We also checked what the effect of BPE or byte pair encoding operations for subword segmentation. So with 15,000, 30,000, 85,000. We used two different mini batch sizes of 8,000 tokens or 16,000 tokens, which meant using one GPU or two GPUs. And we decided to experiment with the embeddings for Swahili and English, and we decided to tie them or not tie them. So using all this, we did a grid search, and the common conditions were we used early stopping very based on the perplexity of the development set. But we had a patience of 5 epochs to see if things would improve after a minimum. And we selected as a checkpoint the one that had the best blue score on the development set. This is quite standard, I think. So the best performers for English and Swahili was a recurrent architecture, 30,000 BPE operations, tied embeddings, and mini batch size of 8,000. Whereas for Swahili to English, the transformer was better, but it used 16,000 tokens. We also decided to use the monolingual data and see if we could leverage their help in view that we had very little corpora. So we used iterative back translation. First, we trained the English, Swahili and Swahili English systems using only parallel data. And then we would translate monolingual data in either direction using the reverse system to generate synthetic source text. So we first selected 5 million sentences from New Scroll as English monolingual data, and we only could use the whole Swahili corpus as monolingual Swahili data, the one we crawled. So we repeated 3 times, basically increased the monolingual data, back translated, added to the synthetic part of the source data, and retrain. And then a latecomer was the new scroll data where it came in late, and we added them to the monolingual data and did that in one turn. Okay, so I'm gonna also show you another thing we leveraged. We had some linguistic resources for Swahili. We were lucky to have that, and for English. So we used interleaving of morphological tags between target words during training. So during training, we will just insert morphological information in the training training sentence, as in the example. For example, the sentence "Anifunza Sheria," which means he's studying law, was turned into vfin for finite verb, and then the breakdown of Anifunza in three parts by BPE, and then the label for noun, and then Sharia. And we did that also with English. We used 3-tagger trained on the Helsinki corpus of Swahili for Swahili, and we trained the Stanford tagger for English. So these are the results we got. Our results with only parallel corpora were successively improved, at least as regards automatic evaluation measurements such as BLE and character F2, were improved as we added more back translation data. So this is one take-home message here would be it is nice to add some monolingual data when your bilingual data is reasonably big, but not completely, but not big. I mean, but not too big. In the sense that if you have enough bilingual data to do something reasonable, then monolingual data will help you. After the 4 iterations, we also added new scroll data for Swahili, as you can see, and then we also added the part-of-speech tags. As a result, the systems are, another take-home message is that the interleaving of part-of-speech tags is helpful. And also that comparison with Google Translate at that time showed that our systems were competitive with Google Translate and even outperformed it according to BLE and character F2 in the case of English to Swahili. But we also had to do some manual evaluation or human evaluation. So we did two things. One thing we did was direct assessment. As you know, this expresses a subjective agreement with some questions or some statements. And in this case, there were two questions. Empty output expresses the meaning of the reference, or empty output is well-written, grammatical, and fluent. So the first one is adequacy, and the other one is fluency. We showed 2005 English sentences professionally translated from Swahili into English from Deutsche Welle articles. And we added also 5 calibration examples, which were meant to check how the annotators were doing. And by removing the 10 warm-up sentences that we showed them, the 4 evaluators evaluated for 2,000 sentences each. Direct assessment is known to have a reasonable correlation with post-editing efforts. So this evaluation was meant to assess how good the system would be for content creation. And the results for evaluators 3 and 4 were not consistent due to the problems in the calibration. And also the results of evaluators 1 and 2 are very different. The only thing we observed was a weak positive Pearson correlation among the evaluators' answers, but it's hard to extract reliable conclusion. So this for the content creation use case. Then there is the news monitoring use case. So here we're evaluating gisting, and we use a technique called gap filling, which basically tries to measure how much does machine translation output assist in restoring, filling, or words that had been deleted from a reference translation. So you get a reference translation, you delete some words, or you put some gaps, and then you show the machine translation and you ask people to fill the gaps. So that's a measurement of how useful is the machine translation in that task. We had professional English translations of 30 Swahili sentences from the Deutsche Welle articles. About 20% of content words were removed from each sentence. And we compared our system, the gourmet system, with Google Translate, and also with no machine translation assistant, like wild guessing without any help. And we had 17 evaluators, and we collected their success rates in the range 0 to 1. The graph shows that when they get no assistance, the evaluators are able to fill about 25% of the gaps correctly, and it's only when they get machine translation assistance that they get something better, something like 0.65. Although, as you can see, there's a big dispersion among different annotators. As a result, you can see there's no conclusive result about Google and Gourmet, but it looks like Gourmet is perceived as more widely different by the different annotators, but very similar overall to Google. So what we've done, just 3 slides to summarize. First, we put together a new parallel Swahili to English and monolingual Swahili corpora that were harvested from the web and cleaned. Deeply cleaned in the case of the parallel corpus. We use the parallel corpus to train the Swahili English systems and English Swahili. And we use monolingual data to iteratively improve them via generation of synthetic source data for back translation. And then we used linguistic resources, in particular part-of-speech taggers, to improve the systems even further. We perform manual evaluation in addition to automatic evaluation. So what we got is automatic evaluation on a news test corpus, which showed us that we're doing quite well because we're similar to Google Translate or even better in some case. We got human evaluation for gisting, which meant that our systems are comparable to Google. And we also did some manual direct assessment evaluation, but that was inconclusive. And we published the corpora and machine translation models for both language directions. Things we should try. We should perform a better evaluation for the content creation scenario. So we're thinking of ways of doing this. Then we should adapt modern approaches to monolingual machine translation to make up for the scarcity corpora. In particular, semi-supervised methods should be explored further. And one thing that was missing is that we couldn't make it work. We had a tool, we couldn't make it work. Perform linguistic segmentation of Swahili verbs as a preprocessing step because they are loaded with information about surrounding words in the sentence. And that's all. Thank you very much.
All right, thank you, Miguel. We have one question has come in so far, and so we are waiting. Go ahead and put your questions in. This first question is, I am curious to know, how did you decide which words to delete for this testing? And I believe this is referring to the gap filling testing.
Yeah, the gap filling paper is cited in the let me see here, down there. It was published in WMT 2018. What we do is we use we delete 20% of content words, and making sure that we don't delete two content words that are together. So we always have a non-content word in the middle, and we do that for 20%. We experimented in the paper that it's cited there with using entropy and other measures to delete the most difficult words, but it didn't make much of a difference. So it's basically 20% of randomly chosen content words, as long as they are not together and are next to each other.
Okay. The next question is, it's interesting that the best network architecture, RNN or transformer, was different for the two translation directions. Were the differences in performance large?
It is hard to assess performance. We didn't really compare. In the automatic evaluation, we have different BLEU scores, but it's well known that you cannot compare BLEU scores between different target languages. And in particular, in the case of Swahili, which is an quite inflected language, and then BLEU may be giving you a wrong measurement. So it's hard to compare performance. Real performance, we didn't do that because we only checked one direction in each kind of evaluation. So we did direct assessment from English to Swahili and gap filling from Swahili to English. So I don't have any hard and fast performance figures to hold on to. So yeah, it is. I find it hard to explain why one architecture was better than the other.
Okay, thank you. Other questions? Oh, I forgot. I'll check the chat too. Okay, nothing there. I was wondering what has happened to this solution since you wrote the paper? Has it been further tested? Is it being used currently?
I don't know if it's being used because, as you see, it was basically similar to commercial solutions. But we have been collecting more evaluation, or at least it's planned to collect more evaluation data. In the Gourmet project, we change languages every 9 months. So Swahili is kind of done, but maybe we will return to it, and we should pursue the things we should try that were in my last slide.
Okay. This is a clarification to the second question. It says, I mean the difference in BLEU or CHRF between the two architectures for each translation direction, not across translation directions.
Okay, I don't have that data because I'm afraid we did an automatic grid search, so we only have the best results. But I could dig them out if the person who asked the question is interested. We can try to dig them out because that's probably on the log.
Okay, thank you. Further questions? Next one. This is another author of the paper says it's around 1 BLEU point, not a huge difference.
Okay, thank you.
So yes. And the original asker also thanked you for the answer. So. Okay, further questions? Then I'll ask if you do a new language every 9 months, will you be applying the same methods to the next language, or have you been applying already?
Okay, what happens is that for each language you are in a different situation. For example, we were lucky for Swahili that is low resource, but not so much. If you see here, we already had about, let's say, 200,000 parallel sentences in Opus for Swahili. Okay. And then there was also the Sawa corpus, which is we were allowed to use it for research. I think some of the languages in Gourmet start much worse than this, with tens of thousands or even less data, very dirty data, very noisy. So we have found it hard to exactly transpose what we've done for one language pair to the new language pair. So each language pair has its own life. For example, there's a language we've been trying, Tigrinya, which is very hard to find any resources for it. So we couldn't use this because to use, for example, back translation, you need to have something that translates reasonably to start with.
Yep. Okay. And the next question was, what other languages are you going to be covering in Gourmet?
Okay, the languages are decided. If you look at the Gourmet website, we have been doing, so we are now in the 3rd cycle with 4 more languages. We basically are languages of interest for Deutsche Welle and the BBC. So we have languages like Hausa or Igbo, Amharic, Kyrgyz, and also kind of, I would say, easier languages like Macedonian or Croatian. So we have a mixture of languages of interest to our media partners, and there's a wide variety of situations in which we find ourselves.
Okay, thank you.
Thank you.
We have time for another question or two. Would you be training pure character models for these?
Apparently, what we found that so pure character models would be the same as doing no byte pair encoding. So it would be 0 operations of byte pair encoding. And so you embed your characters, you learn embedding for your characters, but they don't carry, it's hard for them to carry information which is useful for translation. Of course, the information is there in the context with other characters, but we haven't tried. I don't think we have tried. We tried in another language pair. I think it was English to Kazakh, and it was no good. The system has to learn too much when you are only shown character sequences.
Okay, thank you.
Thank you.
If there are no other questions so far, I do have one more. This is from Antonio Toral. I hope I'm not abusing my privilege here. He says, given the limited amount of parallel data, what about using data from additional languages? For example, via transfer learning or using a pre-trained model such as MBART?
That's a terrific idea. MBART models, as Antonio knows, are quite big, and it's hard. You need big machines to be able to run. You can run smaller models, but they are hard. But yes, this is clearly something we should try transfer, and also we're also trying other things. But transfer is something that we are probably trying. It's a big project, so many people are working in many things. So probably some people are trying. I'm sure that this is being tried between Amharic and Tigrinya because they are related, and Tigrinya is very low resource.
Okay. Thank you. I just got curious about the Gourmet languages. Are your customers using any of these so far?
Yeah, this question was asked before. Are people using the Swahili? I don't know. We don't know.
Okay,
I know they have evaluated them with the real journalists, and the data comes from there. but I don't know if they're being integrated or not.
Okay.
Probably some of the authors if some of the authors is listening here, maybe they know, but I'm not aware of any integration so far.
Okay. All right, then thank you very much, Miguel.
Thanks.
And we will move on to the next one. Anybody who has further questions for Miguel, hunt him down in Slack, or you can put questions, leftover questions, into the user track channel of Slack.
I need to know how to stop presenting.
Share, I think it's share screen and unshare or something.
Yeah, let's see if I can. Yeah.
Or else I can.
Could you kill it for me? Because
I'll try to kill
I don't
it.
get the button. Yeah. Thank you.
All right. So, and then I'll just stop sharing. All right. So our next presenter is Karolina Stefaniak, and she's going to tell us about testing of the use of machine translation by Polish translators in the European Commission. So I turn it over to Karolina.
Yes, hello. I hope you can hear me and that you can see my screen.
Yes, both are just fine.
Wonderful. So my presentation is going to be far less technical. I'm a translator and I work as a quality officer in the Polish language department at the Directorate General for Translation of the European Commission. And I would like to share with you the results of my analysis, which I have been conducting since 2018 on the use of and the usefulness of neural machine translation as a translation aid by my colleagues in the Polish language department. So basically my observations and conclusions concern the English-Polish language pair in the Commission's neural machine translation system, which is called e-translation. So I myself, I'm a big fan of technology. As I said, I'm a translator and I would never say no to tools that would free me from boring, from repetitive tasks that even our very interesting job includes. It's like searching for previous translations, checking numbers, searching for terms, basically translating something that has already been done. And I truly think that machine translation might be one of such tools. Of course, in DGT, we have at our disposal a number of many tools, of course, translation memories and a terminology database, which are integrated in our CAT environment. And the machine translation that you use is provided during the pre-processing of the source text, and it can be included as a resource to complement the translation memory if the translator wishes to do so. So until 2017, it was produced by MTITC, which was Commission's statistical machine translation system. And since November 2017, it is generated by eTranslation, a neural machine translation engine. Statistical machine translation was only partially useful for the English-Polish language verb, actually not so much. So obviously with the introduction of e-translation, the question arose as to how useful neural machine translation actually is for translators as far as productivity and quality of translation is concerned. But unfortunately, studies on the performance of neural machine translation that involves Polish were very limited, are still very limited. And of course, since the performance of neural machine translation depends on the particular language pair involved, so a simple extrapolation of to the English-Polish language pair of the results obtained with another language combination is not really possible. So therefore, in my department, I decided to conduct an evaluation on the potential benefits and risks of using neural machine translation as a translation aid, and I wanted to concentrate in particular on the efficiency of post-editing and the risks to quality. So for the purpose of this evaluation, I recruited 9 colleagues and I asked them to always to work as usual, but always choose the machine translation when they were downloading translation resources, and to use it for all the so-called new segments, that is segments that didn't have a translation memory much, irrespective of the text to be translated. I also asked them to put down any comments and opinions regarding the quality of the neural machine translation output, including examples of errors for each translation assignment. So this data gathering period lasted 3 months, from July to September 2018. And in this period, each of the translators translated between 1 and 13 texts, which varied in length from 1 page to over 150 pages. And they covered both legislative and non-legislative texts from a variety of subject domains. So I think the text types and the subject domains, as we usually translate in DGT, were quite well represented. In the end, for the further analysis, I could use 48 texts, 22 were legislative texts, and 26 were non-legislative texts. Of course, this was too many texts to do a qualitative, like, human analysis. There are too many pages. So firstly, to get a rough idea about the quality of the machine translation that we are dealing with, the quality of the text in the sample, I asked our machine translation unit to calculate the translation edit rate for each raw machine translation segment in the sample, using, of course, the final translations produced by human translators as a reference. So then I calculated the average for the individual text, the median for the text and for the sample also as a whole. And I counted the share of segments that did not require any changes. And I differentiated between legislative and non-legislative texts. So you can see in the table that for the English-Polish language pair, our neural machine translation performs much better for legislative text when compared to non-legislative text. And legislative texts obviously are like regulations, directives, decisions, and so on produced by the Commission. Non-legislative texts are other texts, for example, various kinds of reports or letters to member states or text for web pages, leaflets, and so on. And of course, this result may be explained by the simple fact that, well, in general, machine translation performs better for standard repetitive texts, which feature characteristic terms and phrases. This is typical for most legislative texts that we translate in DGT. And it doesn't give equally good results for texts containing new terminology, new words, rare words, idioms, metaphor, proper names, and so on. And this occurs, of course, much more often in non-legislative texts. So obviously, this is like a very simplistic, well, maybe not simplistic, it is a simple view because the automatic quality metrics show only just one aspect of the picture. For example, they say nothing about the reasons for the edits. They don't capture the cognitive effort of post-editing. Of course, some corrections may be more demanding than other. And this is, of course, problematic when we want to evaluate neural machine translation in this way, because neural machine translation produces beautiful, fluent, grammatical sentences that may still contain serious accuracy mistakes. So another problem with metrics like this is that even minor errors may require substantial changes to the machine translation output, or the other way around. Minor edits may suffice to correct a severe mistake. So in other words, this technical effort of a translator may not necessarily correlate with the speed at which the translator does the post-editing. So obviously some more analysis are needed. So this is just the start. So to have a better picture on of the usefulness of our neural machine translation, I wanted also to analyze the types of errors found in the raw machine translation outputs. As I said, some errors have more impact on the quality of the final product than other errors. So in my 2018 analysis, this data about the errors were basically gathered by means of feedback from translators performing the post-editing and some non-structured analysis of the data that I gathered. So my colleagues basically reported that, yes, neural machine translation produces fluent text with few linguistic errors. This is really good because statistical machine translation was notorious from the mistakes, the linguistic mistakes, and we spent lots of time just correcting the endings. But at the same time, neural machine translation, basically the output of neural machine translation lacks consistency, and that makes ensuring the textual coherence much more difficult. Moreover, the accuracy mistakes produced by neural machine translation were often difficult to detect, and only a careful comparison with the original could reveal the mistakes. So this is a serious risk to quality. Also, errors in terminology were reported to be very common. This ranged from deprecated obsolete terms chosen in terms of the preferred ones to, of course, choosing wrong equivalents for a given context. And mistakes of this kind were very common, especially for single word homonyms. For example, stock may have two meanings. It may be a fish stock, it may be a financial stock. A human translator knows which type of text he is or she is translating, and the machine usually mixes it. This type of terminology errors is also an example of errors in consistency, since terms need to be translated consistently. Inconsistencies may occur between sentences, across sentences, or even in the same sentence. In the second case, they are easy to spot, but if you have 150 pages with basically inconsistent terminology, this is also very difficult to correct and to keep this consistency. So these findings basically are consistent with the literature on the subject. So these two types of errors, accuracy and terminology errors, could be considered typical for neural machine translation. But the issues mentioned in the feedback that seem specific for English-Polish were especially wrong word order, which is calqued from the original sentence, and lots of errors in verb forms. We have in Polish tense, voice, aspect, or mood. These are the elements of verb, and this is usually what machine translation gets wrong. And pronouns were often mistranslated, also due to their ambiguity in the English original, which had to be resolved in the translation to Polish. We have, for example, genders. So we have formal, informal personal pronouns. So the simple you may be translated in like 9 different ways, depending to whom you're addressing the text. Not to mention the impersonal you, which can add like a number of other possible translations. Also specific for the context of DGT, when we translate legal acts, were also very frequent mistranslations of the titles of legal acts, because they were like retranslated, and they of course should have been quoted as they had been published. And the same was true of quotations. Our text also contained lots of quotations, including hidden quotations. This also cannot be retranslated, even if it's like still accurate. It has to be basically quoted as it is. Also, when confronted with abbreviations, proper names, given names, Latin names, chemical names, and so on, the machine translation, neural machine translation can get very creative, producing lots of errors, from just misplacing letters to producing non-existent words, sometimes with nice comical effects. My favorite to this day is new berries in maternity words instead of newborns. This is comical but easy to spot. Misplaced letters in a chemical name or in a given name are much more difficult and have a much more higher risk. So this was the analysis from 2018. This year, at the beginning of this year, I conducted like another analysis of the errors on the quality of neural machine translation. This was for a different purpose. And I conducted this analysis on 200 machine translated sentences, which were part of a bigger sample and which had performed worst in the automatic evaluation. So again, accuracy mistakes were most common, accounting for like over 40% of all the mistakes, which alone shows that the machine translation output still needs to be used with caution. So I don't really see this human parity that we talked about yesterday, at least not in DDT. We are still far from it. So far, I've been talking about the risks of using neural machine translation, but of course, we are using neural machine translation. We don't want to get rid of it, so there must be some benefits. And of course, the first benefit that basically has been the driving reason for developing machine translation is, of course, the productivity gain. So the hope that using machine translation will speed up our translation process. So productivity gain when here we use translation memories as well. So basically it's the difference between the time necessary to translate a page only with the help of translation memories matches and the time needed to translate the same page using both translation memory supplemented with machine translation suggestions. Unfortunately, in DGT, we don't have sophisticated tools that would enable me to track what my colleagues are doing and how long it takes. So I had to adapt a much simpler approach to measuring this potential productivity gain. Basically, what I have performed is were like small scale tests, again with 6 colleagues whom I just asked to, I gave them several sentences, and I asked them to translate some of them to post-edit other sentences. And I chose the sentences for my sample according to this quality measured by the automatic metrics, because basically I also wanted to test whether there is like kind of a threshold above which the threshold of quality of machine translation above which the post-editing takes more time than translating from scratch. I timed my colleagues during both activities with a stopwatch, and then I basically averaged the results. So it was very simple, but it was not going to, it just was supposed to give us like a first impression about how whether using machine translation actually is capable of making us faster. Of course, to no surprise, the average post-editing speed was higher than the average translation speed, but this difference was not really big. 0.32 words per second for post-editing, 0.22 words per second for translation. And then I basically calculated this potential productivity gain. I assumed that an average page is 350 words long, and it has 50% translation memory match. This is the average that I had from my sample. Because obviously, if you have no translation memory matches, your productivity gain will be much higher than if you have a 90% match for a page or for a text. With these assumptions, again, 350 words for a page, 50% match, I arrived at the number 4 minutes or 17% per page. This is somewhat consistent with a few other results that were done on DGT text and DGT translations. It's really not that much, but it goes in the right direction, let's say. So, of course, these results do require some comments. As I already said, post-editing speed does depend on more factors than just the quality of machine translation. So firstly, this post-editing speed varied greatly between translators. So there were faster translators, slower translators. This is very individual. It all depends also a little bit of how well translators use the keyboard, how fast they type, and so on. But it also, I didn't notice also any difference between the quality of machine translation as measured by the translation edit rate and the post-editing speed. I found no correlation, and so I concluded that, like, on average, basically all segments produced by eTranslation, our neural machine translation system, are suitable for post-editing. Obviously, some were more suitable, some less suitable, some were perfect, but on average, I couldn't establish any threshold to say above which there is no reason to use machine translation. Rather, actually, while observing my colleagues during this small-scale productivity test, I noticed that this post-editing speed depended on something else. Firstly, depending on the syntactic complexity of the sentence, not just the length of the sentence, but how complex syntactically the sentence was. And it also very much depended on the terminological density, that is how many terms it contained and how many references it contained that needed to be checked. Because even if that translation is perfect, you usually have to check if the quotation is right, if the title is right, if each of the terms is right, and so on. So this also takes time. This is not doing automatically. So even if the end the translator decides that it's fine, it's perfect, it still takes time. So it's not just a simple quality of machine translation. There are other factors at play here that need to be taken into account when we think about boosting our productivity with machine translation. And also I noticed that translators who are competent in a given domain did not have to do as many checks, obviously, as colleagues who are not familiar with the subject. So obviously what follows is that post-editing speed depends also on the domain competence, which kind of means that if we have like new translators coming, they probably shouldn't start with using machine translation because it will not make them really faster, but they will first need to learn how to translate, what resources to use, so that they can make an informed decision when they are confronted with a machine translation later. Since 2018, now we have 2020, so our neural machine translation engine has improved, maybe not drastically, but still it has improved, so it is possible that the productivity gain now has also improved. But even if it's not the case, we have to remember that time is not the only potential gain of using machine translation. Many colleagues doing this analysis with me remarked that even if machine translation does not make them faster, it still makes translation easier. Some even considered machine translation suggestions as inspiring. On the other hand, they also pointed out to the risk that when confronted with ready translation, existing translation, it was much harder for them to come up with other better solutions, because machine translation kind of directed their thinking in a certain direction. This is also important because whatever we translate, first of all, feeds into the text functioning in a public domain. So we are kind of influencing the language that is out there, and we produce many texts. And on the other hand, whatever we produce may be used again to train machine translation. So if you produce suboptimal translations, we will get worse machine translation results in the future instead of better. So this is also something to take into consideration later.
Okay, Carolina, excuse me, you have 1 minute.
Okay, I'm going to conclusions already.
Great.
So what I want to conclude is basically that requirements placed on DGT translators, especially the requirements regarding the quality of the translation of legal acts, are higher than the usual requirements on the translation market for text meant for publication, because mistakes in legal acts impact not only DGT's image, not only Commission's image, they really have legal consequences. So in order to use machine translation safely and efficiently, certain conditions need to be met, concerning, among others, text suitability and this proper incorporation of machine translation in the translation workflow that would reduce maybe translation effort. But still, translators need to stay at the center of the whole process. They need to maintain agency of their working methods, of translation choices, and it also includes a choice not to use machine translation if they seem it's going to be detrimental. So in order to make these choices, we need more in-house research to determine what works best in our DGT working environment, in for our translators. But also at the same time, we need this research to mitigate the expectations of our clients, and I would also say of the general public, because the increased visibility of machine translation creates the impression for some that the translation is basically a simple activity. It's available at the push of a button. Human involvement is minimal. So as a translation community, we need to make sure that they understand it is not, and then they understand, the proper role of translators. And to conclude, I do believe that technology needs to be seen as our ally. It's not an opponent. To refer also to the chess example from yesterday, in 1997, Deep Blue beat Garry Kasparov at the game of chess. So it is now generally accepted that in this one-to-one contest between computers and human chess players, the machine will always dominate. Fine. But apparently, it has also been shown that human teams of chess players with access to multiple chess algorithms are able to outmatch any single chess-playing computer. So I believe it's the same for machine translation. We cannot engage in a race against the machines because we will fail. And what we have to do is to race with the machines. Thank you very much.
Great. Thank you, Carolina. There are quite a few questions, so we're going to jump right in. The first one says, 9 translators were recruited. How many translators are currently working at DGT for English to Polish?
Yes.
Go ahead.
In our department, we have now about like 45 translators. So basically, this is basically, it's not really rigid research, because it has to be done while we normally performed our duties. So I didn't want to force anybody to participate if they didn't want. So I asked my colleagues who want to participate, and I had 9 volunteers. So I took all 9.
Oh, okay. Yes, the next part of the question said, were they excited or reluctant? And I guess if they were doing it on a voluntary basis, then they were all excited, I suppose.
Yes, they were excited, but not all of them were like pro machine translation. Some of them were actually against, but still, you know, they wanted to show this attitude also by participating in a sense. So it's not that all of them were very happy about machine translation, or I don't know, very positive about machine translation. So there are some like people with negative attitudes as well.
Yep. Okay. Next one. When evaluating the documents, did you consider asking the evaluators to do a document level evaluation?
No, at that time, no. Well, basically, they were, well, what they were supposed to do, they were normally using machine translation while working, so correcting whatever they needed to correct. They were also writing down some like their opinions on the usefulness or the quality of machine translation as a whole, and this was based obviously for this particular text. So in that way, they were referring, yes, they're kind of evaluating the whole text. They were not evaluating single segments. They were writing down or communicating their yes, opinions on the whole, based on the whole text that they encountered. So for some text, like for web text, they were saying that it was not really very useful. For some text, they said, yes, this was fine. It seemed that it helped me a lot.
Okay. Next one, have you found if syntactic complexity has an impact on post-editing speed because it has an impact on MT quality?
It's no, it may have some, it has some impact. I didn't measure it exactly, but it seems that basically if you have a long syntactically complex sentence, it takes time for a translator to read and understand it first, and then read and understand the machine translation, and then basically decide whether it's correct or not. So this this alone takes time.
Okay. Here are 2 questions about the productivity test. One person asked, how much is several? You use the term several sentences. So how many is several sentences?
There were very few, actually. I think there were 12 or 14 sentences, because basically I took my sample and I chose sentences from like good quality, let's say translation edit at edit rate 0, meaning no change was necessary, because I wanted to also see how much time translators needed to process them. As I said, you know, if this is like a long complex sentence, it still takes some time. And then, you know, went up with more or less quality 01, 02, 04, and so forth. So I had, I think, like in the end, 12 sentences for translating from scratch, and 12 different sentences from post-editing.
Okay. And also on productivity tests, were the translators already experienced in post-editing, or was this a wholly new activity for them?
So it was done in 2018 and in July, and neural machine translation was introduced in basically, well, for sure, like in June. So I wouldn't say they were like very experienced. We were using statistical machine translation before, really on a voluntary basis. So maybe a few people were using it, but since it didn't produce really as good results, I would believe none of them was like truly proficient in post-editing. No.
Okay. Have you any idea how many segments are translated from scratch or based on MT? What is the percentage of matches you get from TM matches?
Well, as I said, our sample on average said that it's like roughly 50% is already comes from translation memories. So we have 50% that are like up to grab by machine translation. At this moment, I believe most of my colleagues use machine translation, and they use it in this full segment mode. So whenever there is like nothing, they prefer to have machine translation for post-editing than use it in a different way. There are a few translators, they don't. Most colleagues who work in the web translation unit, because the web translations are quite specific, and they prefer not to use machine translation at all if they translate web content. So I would say that really, I think for the whole DGT is probably like around 70% uptake of machine translation. But okay, please don't quote me on that.
Yep. Do you think there might be a correlation between negative attitude towards MT and over post-editing the MT output?
Yes. Well, I think in general, over editing is whether it... well, the more positive you are, yes, you're probably more willing to accept, but it's not also the machine translation by basically your attitude toward language in general. But I do observe that very many colleagues over-edit something that could have been left as such. But as I say, this is a very difficult question to assess, because we not only have to produce a text in a deadline, we believe we have some responsibilities of what we put outside. And although the machine translation, maybe I did some workshops on machine translation, and one of the exercises was basically to show machine translated sentences. This was a text, and I showed sentence by sentence. And we discussed whether it's suitable for post-editing and so on. So most of it, and then I showed the same sentence translated by a human translator who didn't use machine translation. And usually the reaction was, ah. So it's basically like, you know, this wow effect, something that is correct, accurate, fluent and everything, and it's fine, still can be translated in a better way that still seems more natural. And if not confronted with machine translation, the human translator might have arrived at the solution. And some texts actually require this type of like human touch. The question is which text and where can we say stop? And this is still something we are working at.
Okay, there are some more in here. Many congratulations, by the way, for a good presentation. But I'm going to leave with this one provocative question that maybe is for everyone to just think about. Perhaps it's time to drop the fluency aspect for NMT. We already know it's fluent, and just focus on accuracy.
Yeah, it's a very good question. It's fluent, but it doesn't mean it's still natural altogether. Because as I said, it may be accurate and it may be fine, but it's not something how people communicate, how people write text. This has to do something with other functions of text that purely informative text, for example. And for some texts, this accuracy dimension is fine, but still very many other texts have other functions. And I still think this fluency is still important there, especially when we regard the influence of text, of machine translating text on how we speak, how we write, and in the end, how we translate. But I think it's a very good provocative question. I would like to, I see who asked it, to talk a little bit more about it.
Yep. All right. Thank you very much, Carolina, and all of our listeners. As I said, there were a few things still left in the question and answer. If you would like to review those.
Yes, I will. Thank you.
Yep. We will break now for a coffee break, and we will continue again at, I believe, at 11:30 in Western European time. Yes. So please come back at 11:30 and see you then. Carolina.
Yes, that was stressful.
You
Even
did
though
great.
in person, maybe more because of that.
Yep, but I just want to make sure that you open the Q&A and see these.
Yeah, I see that. So now I think there's the last question. Do I type answer here? Do I take it maybe to Slack? What do you think?
Yeah, and that question it came in at the very last minute, so I didn't see that there was an actual question there. Maybe move it to Slack, and
Yeah.
there is a channel for user track.
I think
and then answer that there.
Because it will require lots of typing.
Yeah.
All right, wonderful. It really works very well. I like that.
Yep. Good. Thank you very much. And other presenters, thank you.
Yeah, thank you. See you later.
See you in the afternoon.